So I'm going to do a potpourri of things connected to efforts over some years to try to model the large-scale structure of the galactic magnetic field, try to figure out what it is from the data. It's work done in the last several years, 5 years maybe? I hate to count, with Mikhail Unger, who's here, fortunately, to give a next talk in the session, which will really get more into the nitty-gritty of all the things you have to do a really good job. So the starting data is the SkyMax of rotation measures and synchrotron, polarized synchrotron SOX Q and U observables. And the aim is to learn what that is telling us about the large-scale magnetic field. As you all know and can see from the equations, if anyone doesn't remember, in order to do that, you have to know the thermal electron density in the 3D structure and also the cosmic ray electrons. If you knew that, then you would get information on the large-scale coherent field. In principle, also the random field and the structure even of the coherence. You can ask questions of, is the electron density correlated or anti-correlated to the magnetic field density? And what about the cosmic ray electrons? And is there a striated or anisotropic component or not? So I'm going to just do broad brush stuff, and Mikhail will get into more details. The work that started with work that Ronnie Jansen, a student of mine at NYU, did with me. And this was the data that we used. We actually used mass data originally, or partly mass data. This was the Wmap, this is the RM Sky, mostly NVSS. Anyway, there's some 40,000 RMs. We just pixelized it into HealPix pixels for convenience. And this was the Wmap Q and U data. You add the unpolarized synchrotron, the total synchrotron emission when you go for the random field. And you see that the model that we derived by making assumptions about that, we just took the standard NE 2001 model of the electron density and took a Galprop model of the cosmic ray electron density. And the magnetic field model that we inferred produced these maps, which you see get a lot of the large-scale structure. The structure I want you to start to calibrate your eyes to is this kind of bilateral structure in the RMs, which is characteristic of a halo toroidal field. That's the sort of main thing that drives that. And this is a very characteristic structure, this kind of, again, I don't know what's the right word, bisymmetric pattern, but that's symmetric north and south in Q, and in U, it's also got this anti-symmetry north, but it's got anti-symmetry north-south. And you see that the model that we wound up with, roughly speaking, captures that large-scale structure. One of the really exciting news is in the last days, finally the data for this region of RMs has been released, and now it's there. And so what you see is, this is just a picture off the paper in the web. In fact, what happens if you try to translate, it does show that this is basically red. So this was just to orient you, the model, which is hopefully soon to be superseded with the work with Mikhail. And even though it was as simple a model as you could imagine trying to write down, it had 35 parameters. It sounds like, how could you possibly constrain them? But in fact, when you start to count them, you can. There was a disk field, and at the time, we didn't think we were interested in the disk field, so we just took an off-the-shelf geometry for the disk due to Brown and collaborators. But we FET for the strength of the field in the different arms. We added a toroidal halo field. Originally, we didn't have this, but gradually we realized we had to have it. It wasn't known before Ronnie's earlier work. And then we added an X field, which was sort of a new invention, this is what it looks like. I'll explain why we added it, but it's basically, it's X-shaped, and it's clearly not a physical model because it's discontinued. I mean, it's got this break in the galactic plane. But it was practical for doing fits. You could see what you had to do in terms of what the parameters there were, how far out it goes when it's just sort of gradually opening out, and then what's its asymptotic angle. And then we considered the possibility that the field was striated, that is to say, there was a random component that had been either pulled apart or squished, so it was aligned with the regular component, which would effectively amplify from a empirical or from a model, from a pragmatic standpoint. It was as if you were amplifying the random field relative, the synchrotron emission relative to the RMs, for example. Anyway, so this was the data that we used. There's a slight improvement, as I was saying, on the RMs. Now there's, in addition to Wmap, superseded by Planck, and it's quite then challenging to actually go the next step and try to extract better what the synchrotron emission is, and Mikhail will be talking about that. And another big important unknown are these NE and NCRE, which is an area where we're doing a better job. The thing I want to, this is a Venn diagram of what you have to do. Your goal is the magnetic field. These are the data that you're using. Ultimately, you'd use more data. You'd use pulsar RMs and so on, but we were just starting modestly. But in order to do this, you need to know the cosmic ray electrons and the thermal electrons. But to know the cosmic ray electrons, their distribution actually depends on well, for example, it depends on the field itself, both because energy losses depend on the field and because the diffusion coefficient depends on the field. The diffusion coefficient gets controlled by these things and so on. So to do an advance that's a substantial one, you have to do all of this stuff. Mikhail will describe to you what the status is of that. And meanwhile, I will focus my session on the easier problem, or easier, different problem of finding good functional forms for the coherent field. And it has to be divergence-free. That X field was good enough to start. Well, especially because we didn't expect to find a coherent poloidal part. And we were just describing a striated field, and it was perfectly fine for that. But it turned out there really was a coherent part. So I want to focus the rest of the talk on this poloidal component. First, explain to you what in the data is driving the need for that to be there, and address the question, could it really just be a fake of some structure locally? And hoping to, I would say that the chances are 90%-ish that it's real and that it's not faked. Maybe higher, but in any event, I wouldn't want to bet the house as Reiki Kolb is fond of using as a measure. And how can it be produced? I'm really hoping to get input from people here about that. And then I'll tell you a bit about progress we've made on the functional forms. This is a way to see that there needs to be this poloidal component. So just to remind you, here's this so-called X field that we're talking about. And so as this is the data, and it's the this is the Q again, U, and just the total polarized intensity. No, that's the angle. I can't read what it is from here. It's the magnetic angle in some fashion. And what you want to do is you want to have a combination of fields that you're looking through along those lines of sight in these directions, such that you get this pattern. And so if you had no X field, but you fit all the rest of the fields, use the GF12, this would be your prediction for these things. And you see that they're just completely wrong in terms of the large-scale pattern. And now you add more and more strength in this X field, and you start to see, this is still not quite showing it, but by the time you get up to 4 microgauss, the best fit value, JF12 is 4.5, you see you're creating this pattern here and there. If you go higher, you start to sort of do too much good. You destroy the pattern in the middle and so on. Anyway, that gives you an idea of what it is in the data that is calling for the X field. You might say, well, what about the shape of the X field? That looks sort of, do we like that shape? And this is to show you pictures of external galaxies, which was the original reason that we put in an X field. But as I said, expecting that it was going to be of this striated random field type. And so because it's well known that in external galaxies you get structures like that, that was the motivation. And if you look at this X field as an observable looked at side on, you see that the X field that we derived by looking from inside out in our galaxy corresponds actually quite nicely in side view to what those galaxies that we see outside look like. That doesn't prove, of course, that this is coming from a coherent structure, totally separate. Okay, so I hope I persuaded you that it's, or at least you have some feeling for this. The main things I want to address in the end are these questions, and I'm going to talk about now the toroidal field structure. So, as I said, or I guess I didn't emphasize it, when you just fit for the toroidal, in this JF12 model, there's a disk field, there's this possible poloidal component, and then in addition, there's a toroidal field in the north and south. And we fit, and we discovered that, Ronnie and I, that the strength of the field was pretty much the same in north and south, but that it was moving in the opposite direction. And even way back then, out of curiosity, I asked myself the question, what would you get if it was produced by differential rotation? And lo and behold, it's got the right sense to be, because we know what direction our galaxy is rotating. And it's got the right sense, and of course that explains roughly why it's the same strength in the top and bottom. So what this slide is about, oh, I jumped the gun. Well, I'm going to talk about, the next slide, I'll talk more about that topic, about where Mikhail and I are taking that. So the one advance that's, I compliment my collaborator for innovating this. This was the model that Ronnie and I used, taking the arms from others. But Mikhail realized that a beautiful way to represent it is in this, what we call a Fourier spiral. And then that gives you a lot of freedom to simultaneously fit for the field strengths and the geometry. Good, thanks. So anyway, that works very well. Other advances we've allowed for the possibility that flux is coming into the disk and out through the halo, but the data doesn't like that. It sort of stays in the disk. We've allowed for a warp and flare in the disk. That doesn't do much. We've tried different geometries of the X field. This is pictures looking sideways instead of that really sharp one. And so I'm very much eager to get input and suggestions for what functional forms to use more generally. This is what I was jumping ahead to. It's very beautiful when you actually put in, you rotate you start with the poloidal field that fits, and then you rotate it, assuming infinite conductivity. Then you get an expression, and then the only parameter that would be left is essentially how long it rotated. Of course, what's really going on physically is that there's a tendency to be rotated from the differential rotation to produce this azimuthal field, and that's, I assume, restored against the magnetic diffusivity, which got set to 0 here. And so the time scale is a way of simply representing it. In the next phase, we're going to, and this is again something for which input will be most welcome, what's a good model of this diffusivity parameter as a function of radius? In any event, if you do this procedure just to get started with a constant diffusivity, this is the halo field, the toroidal halo field you come up with. That was a toroidal halo field that we got in JF12. And in fact, this is equally good fit. And so far, we haven't even used any of this geometry. So what you see is basically to me, it really hangs together very beautifully physically, that's essentially what's producing this toroidal halo structure. The very last thing, quickly I'll say, there's an important question of could we be faked out by local things. And one way to do that is to look at simulations, which people are getting more and more refined, and tomorrow morning we'll hear about that. But in any event, this is an example of looking from different views in one of the illustrious MHD simulations. One of the striking things is that there's not very much observer-to-observer variation. The important thing to take away, and I'm going to be really interested in the talk tomorrow morning, they're very far off. They're far off by a factor of 100 in the RMs because they're both way too strong in the magnetic field, the coherent magnetic field, and much larger in the electron density. And they also, none of the simulations so far produce a large-scale halo. This is another example showing how the simulations aren't producing that. Well, it's always a possibility that we are being faked out. On the other hand, it's also a possibility the simulations haven't yet been refined well enough. So we could say, how could the poloidal field be formed? I was going to draw a picture myself, but there's this thing that comes with Keynote, which I was able to play around with. You're supposed to imagine that these are two colliding galaxies. I have to say, the time scale for forming the large-scale poloidal field that we see is way too long, given the present conditions in the the electron density and so on in the disk, to explain it, to have arisen under present conditions. So how could that be circumvented? Well, one possibility that intrigues me is if you take a model that there was a weak, like nanogauss, or I don't remember now how much lower it could be, magnetic field in the general vicinity that got swept together as a result of the collapse that formed the galaxy, and you just compute what would the field be like. It's very much like the field we see, so that's a possibility. And then another one is that if you ask about what the conditions would be in a merger, they're much more conducive to dynamo. So perhaps that's a sign that simulation should explore the merger history. So I'll stop with that. Thank you. I can run a picture while, you're not supposed to look at the picture, you're supposed to ask me questions. But that's just an explosion at the center of the galaxy, how the cosmic rays would, the electrons, for example, or it could be high-energy cosmic rays if there was an explosion at the center of the galaxy, how they would dissipate in time.
Cool. So we have time for a couple of questions. Axel?
Say you don't need any different turbulent diffusion when you wind up the...
No. I said we're just in the preliminary stages of studying it. We showed that it gives qualitatively the right picture, right, but we haven't yet explored.
But it would be overwound, right? It would be far overwound.
No, I think what I imagined, but maybe, again, you may disabuse me of this notion. What I imagine is that as the field gets twisted around, there's more and more restoring force, so to speak. And in effect, the field lines slip in the differentially rotating medium. The way we modeled it, we just let it rotate for a certain amount of time and then quit. And the time that made it fit well, the observations, was 70 megayears. So clearly, it could be a fast enough process.
When you say restoring force, you mean Lorentz force?
No. Well, talking about microscopically, I think I would agree with you, but one might describe it differently in MHD terms. So for instance, a step that seems a natural next step is to try to come up with some sort of parameterization of what the diffusivity would be as a function of radius and height, have some idea, which we're looking forward to input from this audience, of what would be a reasonable value for it to be, and see. I think that will probably improve the fidelity.
Alex?
Is kinetic model to test, in fact, because you mentioned this local structure, whether we can be messed up by that, and what we've been doing recently, and I hope to give you some flavor of what we are doing tomorrow, is a three-dimensional structure of magnetic field can be obtained using synchrotron polarization gradient using Faraday depolarization.
I'm looking forward to
And
that. Yeah.
this would be really interesting, especially because you have these predictions.
So, well, we'll find out tomorrow, but some probes are much more useful for the near region, and that could help us understand to what extent the local environment could be creating this apparent large-scale field. Okay.
Great. Well, thanks
We
very
actually
much.
have a question from the web.
Oh,
I'm going to try my best here. This is from Stephen Hackstein. Do you think that the poloidal magnetic field is restricted to the disk only, or may it also extend into the halo of the galaxy?
Oh, I'm so sorry I didn't make that clear. No, it's extremely extended. In fact, think of the magnetic field, of the dipole field of the Earth, for example, or of the apple. The apples are well known to have magnetic dipole fields. Anyway, they are very extended, and this one, its field strength drops only slowly vertically. And so it's quite significant even at 3 kiloparsecs. It's almost as big in the center of the galaxy as it is in the very center of the galaxy. It's several microgauss. So specifically by poloidal field, I meant a large-scale field. In our case, it comes from north to south, and it's more or less squeezed in the middle in some slightly hourglassy way.
So he also states, is there any observational evidence in external galaxies, or do some of these theories that produce a poloidal predict that?
There's a picture that I made of the external galaxies. I'm having trouble make it backspace after those big files for the movies. In any event, I guess, wait, it was this way. This picture. This shows these external galaxies for which there's strong evidence for observationally. These lines, these little bars, are sticks, are essentially the inferred directions of the field of external galaxies. And you see all of them have, at quite distances from the galactic plane, they have a component. Now, the thing that was interesting for having invented our model is you might have thought that because our field model has it sort of most concentrated in the center and then spreading, you might have thought, well, that's not what we're seeing. But in fact, in projection, that is what it looks like in the observables. And so, indeed, I would say other galaxies show us, at the minimum, there's that structure at least at a striated level. Whether those galaxies have a coherent orientation like ours does, ours definitely does have this coherent orientation. The only question is, still in my mind, is there some way, some local thing could fake it? Of course, you can always fake it, but it seems to be extremely contrived, as far as I've been able to see.
That question was from Anne, and she has a second question that says, how sensitive
I think we need
is
to
the
move on.
fit to different electron density models?
That'll be discussed in the next talk a little bit.
No more questions over the webinar at this time.
Great. Thanks, Fox.
Not that you really plan to talk about it.
1, 2.
All right, our next speaker is Mikhail Unger, who's going to talk about improved constraints in the structure of the galactic random field. Take it away.
So thanks for having me here. So I will now, Glennis was covering mostly this coherent field, and I will now speak about how we try to infer the random magnetic field component. And so like where we are taking off is what has been done by Ronnie and Glennis in 2012. So what you're trying to do is, again, you make up some global model of the random component of the magnetic field. And this time, what you're trying to describe is the sky map of the synchrotron intensity, the total synchrotron intensity, not the polarized one. So this model back then, so here you see the comparison between the random disk that was modeled and the coherent one that we've heard before from Glennis. So there was a disk component with different arm strength, and then a halo component, which was just modeled as a Gaussian height and an exponential in radius. And you can already see, or like, well, that's at least my intuition, that there's some funny things going on. For instance, you have one arm who has like at the reference radius 37 microgauss, which is a lot, yeah. And what you think is happening is, so here is the sun. This is this very strong arm that got modeled. So this was basically driven to get the total intensity described here in the fan region, which is probably not, well, this extension of this arm, but must be a local feature. And I think evidence is that it's beyond the Perseus arm. So we are trying now to improve on that. And the first thing we looked at now, since Planck came out later, so how does this new data look like? So here you see the sky maps, so the 9-year Wmap base model versus the Planck map, the Q and U polarized intensity and the total intensity. So you can see that here, like, and here shown these are differences now in microkelvin. So you see that there's some calibration issues, maybe in the Planck data, but for sure in the galactic plane, they have order 1 differences here. But now, for the purpose of this talk, what is most strikingly, I'm sorry? This is year 3 data. So I think this should have been better now. Actually, what I'm not talking about, the intensity has not changed by much. Yeah. So if you now compare the intensities between what Wmap derived and this is what we tuned the random field from, and what Planck derived. So this is a huge difference. So here, this is another ratio which goes in the galactic plane up to a factor of 20. Yeah. So you might wonder what's happening here. Well, the thing is that this is like nobody measures really the synchrotron emission at these frequencies at several tens of gigahertz. But these are all data products. So they are deriving this by having a lot of foreground subtraction. So this was the model that was done here in Wmap. So they had free emission. Then everything was dominated by synchrotron. And then, well, at higher frequencies, which we don't care, there comes the dust. This you can do. So if you do this, you can basically derive the synchrotron spectral index from the data itself because you measured at several frequencies. However, if you think that there's an additional component with this anomalous microwave emission, aka spinning dust, and then you can see here in this range that there's so much components that you cannot disentangle them anymore from the data alone. So what Planck then had to do is that they had to assume a spectral index for the synchrotron, and that's how they were then able to disentangle these. And then, of course, the synchrotron ends up much lower because then the intensity here is mostly determined by this spinning dust component. And if you look closer, because how this product was made, so here you have the Haslam map, which is at 408 gigahertz, where you don't have this mess in 408 megahertz, sorry, 408 megahertz, so that, where you're really dominated by synchrotron. And this is the Planck map, and if you look at the ratio, so Planck basically is just Haslam plus free foreground subtraction. Yeah? So there's no, in my opinion, no added information in this high gigahertz Planck data. So what we now will do the following: we will just go and back to the old Haslam, where you have no such problems here with this anomalous dust emission. All right, so now we picked our data product. Now, what do we need? Now we have to specify a 3D model for the cosmic ray electrons, because these are the electrons that are spiraling in the magnetic field when we make the synchrotron emission. So we need their 3D structure. So this is like a cartoon, how this might happen. So the primary electrons are created in supernova remnants and accelerated there, and then they diffuse through the galaxy. Protons, which are also created, can have hadronic interactions and then produce pions, which then decay and in the end give you secondary electrons. I will not talk about this, but of course there's a bit, or yeah, is or was a big buzz about these positron data and the antiproton data, whether or not they're astrophysical or particle physics. But this is at high energies, that doesn't really matter for us. So now, if you want to model these cosmic ray electrons, first of all, you make some assumption about the origins. As I said already, the primary electrons come from supernovae. You have the secondary plus and minus from interactions of protons with interstellar medium. And you might also have at high energies primary electrons from pulsar-wind nebulae. The only data that you basically can tune on, if you don't want to use the synchrotron intensity, which we want to use to measure the magnetic field, is the cosmic ray electron spectra at Earth. Then, as you see in a second, this primary to secondary ratios, like boron to carbon and beryllium and stuff like that. And this then you assume some source distribution. So this is a very simplistic model you could come up with. You say all your sources are in this disk of this height small h, and then you run a full diffusion calculation, including synchrotron loss and other energy losses, to predict the spatial distribution of the cosmic ray electrons. What you will find out that the data does not really constrain the diffusion coefficient and the diffusion volume separately. Yeah, so that's intuitively clear. So you can either have a very small diffusion coefficient and a small volume that gives you the same path length effectively than a large diffusion coefficient and a large volume. So, and this is only broken here by this what's called cosmic clocks by radioactive elements. Okay, so ideally, because the galactic magnetic field causes the diffusion, we would actually like to fit these both together, yeah, make a diffusion model based on a random field. So there's this quasi linear theory where you, in principle, could do it, but we think it's not precise enough to actually count on that. So instead, we are relying on data, which then constrains the diffusion coefficient and its energy dependence. And here, the most valuable data is the boron-to-carbon ratio. Boron is produced in nuclear interactions with the interstellar medium, and carbon is primary. So what you can get from this ratio is the effective target thickness, the amount of matter traversed by these primary carbons. So if this matter thickness is large, then this boron-to-carbon ratio will start increasing. And this is the data. So this is the new, very precise data from AMS. You see that the boron-to-carbon ratio drops towards higher energies, meaning that the effective grammage gets smaller and smaller, which you can interpret that basically cosmic rays are getting, their paths are getting more straight and straight. And in the end, they're just more or less ballistically escape the Milky Way. So from this, you can then derive the diffusion coefficient, which then well, you can fit for this delta, how the diffusion coefficient depends on energy. And with this latest AMS data, you get something very close to 1/3, which what you would expect for Kolmogorov turbulence. Of course, you also need to know to make this kind of inference, you need to know the production cross sections, which, just as a side note, are surprisingly less known at very high energies. That's why we currently performed some new measurements at the SPS at CERN to get more data here. All right, so now you have your diffusion coefficient, you have your cosmic ray source model, so you stuff all this in a diffusion equation solver. There's several programs like Galprop or Dragon or Picard. And then you see like several calculations of the cosmic electrons. You can find the literature. So first of all, you can try what happens if you're using different source terms. This is just a smooth disk where you inject your cosmic rays. And this is a spiral disk. So at low energies, there's some difference. You see the contrast, but the cosmic rays diffuse far enough that this is kind of washed out. At very high energies, because the cooling is so strong, you can see then that this really makes a difference. Yeah, and then it really is important if you're here or in an arm. Yeah. So luckily for our purpose, we are like more in the GeV range for this synchrotron emission. This is not very important, but somewhat. Then, and this is the most troublesome, there's this ambiguity between height and diffusion coefficient. So if you choose a small diffusion volume or a large diffusion volume, which currently cannot be distinguished from the data, you will then have the cosmic rays obviously transported high up in the above the plane or not. And then if you want to model the synchrotron emission from this region, you correspondingly need less or more magnetic field to describe it. So this is currently an unresolved problem. So we are currently improving on this modeling of the cosmic ray electrons. So one really cool thing is that now we have this super precise data from AMS here at these energies. Voyager just left the heliosphere, so we have actually no data outside of the heliosphere. And so AMS is in the heliosphere, obviously. Yes. So you see here that at the low energies, so you have the effective potential that changes the energy of the cosmic rays. So this is the same fit. So this is the fit outside of the heliosphere, and then here with a heliospheric potential. And you can describe the AMS data up down here to the very high energies of Hess. What we're doing now, we are doing 3 types of different diffusion coefficient fitted to boron carbon with different. One has convection, the other one has a exponential decay of the diffusion coefficient with height. Yeah, so we make these variations to check how important is the energy dependence at low energies of the diffusion coefficient. Then for the energy loss, it's not only that you have to self-consistently put in the magnetic field you're fitting for, because this very same magnetic field will cool your electrons. You also need the interstellar radiation field, because the energy density of photons and the magnetic field is about the same, so you lose the same amount of energy from synchrotron and from inverse Compton in a galactic disk. Yeah? So this needs to put in from somewhere external. You need to try several source distributions, and then once you plug in your 3D magnetic field, you can then predict the synchrotron emission at 408 and to 22 gigahertz. So this is then here, for instance, if you calculate this, the effective power law index between the two. Yeah, so you see that there's like a 0.1 variation. Sorry for the small scale, 0.1 variation on the sky of this power law index. Right. And then once you have this, so the most important ingredient here was now to get several flavors of cosmic electrons. Then you can start fitting the data. So also here we did some improvement with respect to 2012 fits. So our model now is, so what we really want to model is the intensity that comes from the random field. We don't care so much about the intensity that comes from the coherent field, yeah, because this we just take from the data. So this is the polarized intensity. Now, given the polarization fraction, about like 70%, you can say that the total intensity, yeah, is the sum of the one from the random field, some free emission here in the galactic plane, and then this coherent one. If you add them all together, this is your model prediction, which you then can compare to the data. And so this is some very preliminary where we just had a symmetric spiral and some a Gaussian halo field. You see then this is the Haslam intensity, and this is our model. And again, this is very preliminary, but you see that in this way you can really get to a very nice agreement between data and your model, and make a really next step in the modeling of this galactic random field. All right, what's written here? Perfect. Okay, so as an outlook, so now once we're finished with our random field model, and there will not be just one, because all these ingredients are under constraints, so we will have a range of values that we allow for. It would be really nice to test this with the fluctuations of the RMs, which they are also obviously depending on the random field. But not only on the random field strength, they also depend on the coherence length. So if you have a very small coherence length, you will, in the line of sight integral, you will average over many flips. Yeah, so you get small fluctuations in the RM. And if it's a large coherence length, then you will have larger fluctuations. So this is the data, which has not yet been cleaned up. So we are in the process of cleaning up. So there's in this RM data, there's a lot of these NVSS measurements with just 2 frequencies. And then you have this M-pi ambiguities you need to correct for. But what you see is that, as I just said, that if you take now here for the JF12 coherent field with different coherence length, obviously you get different RM fluctuations, which do not resemble very much what is in the data. What you show here, these are stripes in different longitude bins with different colors shown here, like this A, B, C, D, and A. So for sure, this small coherence length does not describe the data at all, and this one slightly better, but also not very perfect. One thing that's missing here, so maybe they should not describe it yet, because this has only the random field, but not the NE fluctuations. So first of all, I think we've seen this morning this big power law on the sky. So the thermal electrons fluctuate themselves. So this has to be propagated into the sigma RM. And there's further complications that one needs to decide or understand what is the correlation between the magnetic field and the thermal electrons. They could be either anticorrelated if this is dominated by pressure equilibrium between magnetic pressure and gas pressure. But there could also be a correlation if there's compression going on, then you compress the thermal electrons at the same time and increase the magnetic field. So these are open problems for this RM study, and I think my time is over, so I stop again here with this different ingredients, where soon we hope to get an improved magnetic field modeling. Thank you. Yes.
Well, for GeV electrons, I agree with you that the diffusion model is applicable. For TeV, I think we should be more careful, at least in a perpendicular direction. We are likely to have super diffusion, Richardson type diffusion on the scale of the injection. And this is approximately 100 parsecs. So I believe that these TeV electrons might lose energy on this scale, and therefore it's some correction that may need to be taken into account.
Oh, that's interesting. Yeah, so for sure they don't contribute much to the synchrotron emission, yeah, because the electron spectrum is so steeply falling. But I don't know, like probably related to this, I never heard about super diffusivity, so thanks. I will look it up. But also, what we don't have here is any anisotropic diffusion. So, and this, I guess, would be also important at even at low energies. Yeah. Sure. But this is another rabbit hole to go down. Yeah. So the question is also with all these numerical expertise here, I mean, it would be really nice to just do a tracking, yeah, and then see what is the effective, given this model, what was the effective diffusion coefficient? But it's very computationally intensive and yeah, can all be done at GeV.
Any other questions?
So first, I agree that we derived the diffusion coefficients of cosmic rays based on a tacit model MHD turbulence. I think it's interesting to apply that to in comparison with observations. Another is you mentioned the rotation measure fluctuations. If you compare it with emission measure fluctuations,
with what fluctuations? Sorry, with
Emission measure.
emission measure
yeah,
fluctuations,
yes.
and then it can help to tell whether this rotation measure fluctuations, including correlation lengths, it can come from the correlation length of the density fluctuations, and it's much smaller than the magnetic field scale.
So you say this is basically what is shown here, right? So well, like emission measure would be Wham, for instance, here. So you say if I plug this into my simulation, I would find that this does not contribute a lot to the RM fluctuations. This is what you expect?
There are observations showing the rotation measure fluctuations, emission measure fluctuations, and they have similar spectral slope, and which is consistent with not this density spectra, but shallow density spectra, which has the small correlation scale compared to this large correlation scale.
Okay, thank you.
Any other questions?
We have a question for the webinar.
Great.
This question is from Anne. And has a question. I have a question about random fields. Perhaps I missed something. In reality, there's probably a range of scales. How should I understand the definition of your coherence length in this context?
So the coherence length is basically comes from the inner and outer scale of the fluctuations. So what we're fitting for is the RMS strength of the total RMS strength of the B fluctuations. The coherence length then has kind of a, if you want, Kolmogorov type of idea behind it, that you have several, that you have a power spectrum of different like modes in K-space. So I'm not sure if this answers the question. But there's the overall strength that causes the synchrotron emission, and the coherence length depends on the inner and outer scale of the turbulence.
Like you're referring to here, it's more or less the maximum scale of the random.
This length is the outer scale?
Yes, that's correct.
For Kolmogorov, it's the outer scale divided by 5, if the inner scale is very small. And
She says, okay, she understands.
Yeah.
Well, thank you very much. This is super interesting. I hate cutting people off. Next up, we have Ethan Vishniak, who's going to talk about the origin of large-scale magnetic fields. Thank you.
Okay. I have to apologize in advance because I didn't cull my slides enough, so I'm just going to skip things at random. And like I said, I apologize. So I thought I'd start by showing a picture of a nearby star with magnetic activity all over it. The question I'm trying to address in this talk is how you get large-scale magnetic fields, which is to say magnetic fields on the scale of the system, like the dipole field and the large-scale toroidal field of the sun. In the context of astrophysical objects, this usually occurs with a lot of small-scale structure at the same time, which I will not worry about too much. The large-scale dynamo problem, in an abstract sense, is something we worry about in stars and galaxies, accretion disks, planets. It's ubiquitous. And computational simulations of the process are difficult, challenging, and occasionally disappointing. It's a hard problem just to solve by brute force. Now, there's a cartoon which people like to invoke, and I've stolen this one. But the idea is that when you're trying to explain a large-scale magnetic field with turbulence, you start out imagining that you have a large-scale magnetic field. And I like to have a weapon in my hand. So you start out imagining you have a large-scale magnetic field, and you have differential rotation, which winds it up and winds it up. And if you just look at the toroidal component, you get these rings. But at the same time, there's some systematic physical bias in the turbulence, which tends to make these rings into right or left-handed spirals, depending on where they are. And then you wave your hands and say reconnection 3 times really fast, and you end up either reinforcing or diminishing the large-scale poloidal field that you start with. So we imagine this is a 2-step process, shear plus the creation of these spiral lines. But of course, it all happens at the same time. Now, the problem with this is that there's a fraudulent thing hidden in it. This part, going from here to here, is a fake. It's easy to imagine this step if you imagine that all the field lines are like little tiny threads and you just do whatever you want. But if you instead envision them as being like, I don't know, rubber bands or tubes or something with finite size, and then you picture how it is that you do something to it, you find that this is extremely problematic. It's like, here, I have this cord here, which I've just disrupted. I apologize to whoever it is. But if I scramble it and twist it around, I can do so easily by moving the ends, but it's almost impossible to do it just by moving the middle. Okay, so the point is, just by moving a cord of finite thickness, you invest all kinds of energy in balancing the twisting on the largest scales with twisting on smaller scales. In terms of equations, so I was trained as an astronomer, so I have a aversion to equations. But in most astrophysical fluids, approximately the electric field is minus V cross B. The induction equation has this simple form. And there are small resistive terms, which we will assume that their exact form is irrelevant. They're infinitesimal. They're not zero because you can break flux freezing, but they're small. So the traditional way of doing this is to invoke Meanfield dynamo theory. You divide the velocity field up into a large-scale piece and a small-scale piece. So for a star, that's like rotation and differential rotation is a large-scale piece, and the turbulence and the convection is the small-scale piece. This is the large-scale magnetic field and the small-scale magnetic field. And if you want to see the evolution of the large-scale magnetic field, you have these pieces, advection of the large-scale field, stretching of the large-scale field, and then you have a coherent electric field due to mysterious correlations in the eddies. And then you have to calculate that mysterious V cross B. And the way to do this was first pointed out by Bouquet, and people have since screwed this up in various ways, but it's a very simple idea, which is that you balance the random decorrelation of those pieces with the time derivative of the systematic time derivative of V cross B, and then you can estimate this as the correlation time times the time derivative. It has 2 pieces, and you do a whole bunch of algebra, and you find that the electromotive force has a piece that has to do with the current helicity tensor minus the kinetic helicity tensor, twistiness of the magnetic field minus the twistiness in the flow lines, times the large-scale field, times the coherence time, and then there are drift terms and dissipative terms. The current helicity, J dot B, it's related to a conserved quantity, which is the vector potential dot B. It's usually treated as a damping term, but it shouldn't be. And then the kinetic helicity is V dot vorticity. It's usually treated as an important driver, but it probably shouldn't be. So a few words about the kinetic helicity. It's a pseudoscalar, which means that if you reverse all directions for a parity transformation, it switches sign, so it's not a true scalar. In order to get a non-zero value, you need to break symmetry in all three directions. So you can estimate it. It's dependent on rotation or shear, the size of the system. You can do this kind of thing. The magnetic helicity, A dot B, is a more powerful tool because it's a locally conserved quantity. It is, let's pause for a second, it is a Chern-Simons symmetry, and it is that Simons. It is the only classical example I know of. It's in the Coulomb gauge, it's gauge dependent, but in the Coulomb gauge, it's more or less proportional to the current helicity, so it has an immediate tie-in to a physically important quantity. You can move it around. It's very hard to destroy it because you can't move it down to small scales to annihilate it. If you separate out the eddy scale piece, then you get a conservation equation for it, which has a term corresponding to moving the magnetic helicity between scales. And the reason that's cool is because the electromotive force here, which corresponds to moving it between scales in the direction of the large-scale magnetic field, is the piece you need to drive a dynamo. So transferring magnetic helicity between scales is driving the dynamo. And, so you can ignore this in a limit where a characteristic rate at which this relaxes to just this term equal to this term. And this is the flux of eddy scale twistiness. There's a famous result, which is now more than 20 years old, which is that if you just set the systematic flux of eddy scale twistiness to 0, which would be the simplest assumption, you turn off the dynamo. So Gruzhinov and Diamond pointed this out, and it kills kinematic dynamo theory. So worrying about magnetic helicity, the first effect is that kinematic dynamos will not get you to a strong large-scale field. Now, it shouldn't be 0. You can define it, a little messy. You can estimate it by balancing its systematic growth with turbulent decorrelation. You can either calculate it exactly, well, just leading order under certain assumptions, but you can also get a fair ways just by saying dimensionally, it looks like this, v squared times b squared, either the shear or the rotation times correlation times squared times eddy shape factors, which are at most 1 and can be small, depending. So for example, in a rapidly rotating star, turbulence is very anisotropic and the shape factor is small. This is a pseudovector, which is to say if you turn all directions around, it does not change sign. And in a thin disk, it points along the vertical axis. So for example, a galaxy will be ejecting magnetic helicity of opposite signs on opposite sides of the disk, which can help drive a large-scale poloidal field, maybe. In other cases, like stars, when rotation and shear are weak, this current will be in the local direction of shear and rotation, or if they're different, some weighted sum. Strong anisotropy can make it point in other directions. So, first of all, why is this important? You can look at this and ask for this generic magnetic helicity current, how long it takes for this term to be more important than the environmentally imposed kinetic helicity term. The answer is 1 eddy turn over time, which means that generally speaking, there never is anything such thing as a kinematic dynamo in a realistic astrophysical system. So we can ignore kinetic helicity. If you want to ask, suppose you have some flux, how do you relate that to V cross B? Well, this has to do with various projection effects. But basically, there are some components which are preserved, which have to do with dissipation and drift. But it's the divergence of the magnetic helicity flux times terms which are proportional to 1 over the large scale field gives you V cross B. So what that tells you is that when the large scale magnetic field is weak, this thing will drive a dynamo very rapidly. And it will slow down as the large scale field becomes strong. Or to put that in other terms, the growth rate for the dynamo is proportional to the small scale random field over the large scale field. This should be contrasted with traditional ways of looking at dynamos as an exponential process where there's a constant growth rate. So for example, for our galaxy, when we estimate the growth rate of the magnetic field of the galaxy from current conditions, that's actually the minimum growth rate. It's been slowing down until it reaches saturation. I'm losing track of time. Okay, I'll speed up. So the third effect of the magnetic helicity is that you can make a large-scale dynamo work this way, but it's not like a traditional dynamo. It goes fast and it slows down as the large-scale field grows. Forget about the MRI. So I don't have a stellar model available. We can imagine a dynamo in a box. And just imagine for a second a star is like a box. You have some shear, some rotation. You can drive a magnetic helicity current in the box. The field will grow, the thing will slow down, and eventually the growth rate will be balanced by the dissipation rate. The dissipation rate doesn't change with time, so it slows down, gives you a saturation, and you can estimate, therefore, the saturation strength of the toroidal magnetic field. And when rotation is slow, you get an expression which is proportional to something like the geometric mean of shear and rotation. Buoyancy changes this slightly, but not in an important way. If things become strong, then the geometric shape factors become enormous, and you end up being proportional to what's basically the convective velocity in the star or the box times the shear over the rotation. That's going to be in rough equirotation with the turbulent energy density. And so moving right along, stars. Here we go. These are slow rotators. Here's magnetic activity. It should be going roughly as the square of the rotation rate, which is what it's doing, and then it saturates at rapid rotation. This is not the X-ray activity, but the actual field strengths measured by Zeeman broadening of the infrared lines, and we see the same effect. So generically, this kind of dynamo correctly explains the way stars behave, magnetic fields behave in stars. I'm going to skip this. Let me just say, if magnetic helicity conservation is important, this is a challenge for a lot of codes, many of which do not conserve magnetic helicity very well. Obviously, with high enough resolution, you will conserve magnetic helicity, no question about it. Spectral codes do better generically than grid-based codes, but you need magnetic helicity to be conserved on the timescale of your dynamo, and that turns out to be very difficult for MRI simulations and not easy for many others that people rely on. So this is an important test. It's an important flaw in many simulations. I'm not sure what to recommend. I've thought a little bit about it, and people can ask me afterwards. summary, if we just ignore kinetic olicity, we get a really nice qualitative dynamo, which explains how stellar magnetic fields work. And we can ignore the whole no-go theorem proposed by Gruzhinov and Diamond. Gives a reasonable qualitative explanation for MRI dynamos and disks, their numerical problems. And by the way, it will give you a very rapid growth of galactic magnetic fields early in the universe because it's not an exponential process, it's much faster. And kinematic dynamos are irrelevant. Okay, I'm done.
Thank you very much. We have time for several questions. Dick?
The title of your talk was the origin of large-scale magnetic fields, but what you talked about was the growth of large-scale magnetic fields. Do you have any comment about the origin of the seed fields?
Yeah, so obviously what seed fields you have for a given object depends on its early history. The problem is cleanest for galaxies because they're natural processes probably involve very small initial fields. I say probably because you can imagine physics in the early universe which would change that answer. But if we stick to conventional physics, then the seed field for galaxies is many orders of magnitude below current. And the only plausible way of getting there is that you get seed fields not directly from the large-scale seed fields that you got, but from the small-scale dynamo generating eddy-scale fields, and then the long wavelength tail of that, plus stretching by differential rotation of the galaxies, gets you in a fairly short time up to about 10 to the minus 7 Gauss. So only a factor of 30 or so below. And that remaining gap can easily be closed by this kind of dynamo. So of all those many orders of magnitude, most of them are probably not a large-scale dynamo problem, I'd have to say.
Other quick. Axel?
You say that many codes do not conserve magnetic helicity. That I could imagine could be true of the people who are running codes with so-called no explicit viscosity, so they have no control over the actual viscosity or turbulent diffusivity. Has anybody actually been able to quantify that? I mean, I know, for example, for pencil code simulations, there's really no problem. But that's also because we advance the vector potential. For us, it's easy to actually monitor the magnetic helicity. For all the other people, it's actually basically impossible to monitor the magnetic helicity.
Right, and so for most
impossible, but
codes,
difficult,
people
not
go back afterwards, and if you harass them, they will try to see how well they have conserved magnetic helicity. My only direct experience in this, since I'm not a numericist, is I've taken advantage of the goodwill of a few people who do MRI simulations for accretion disks, like Shane Davis, and tried to follow the magnetic helicity slice by slice in some of his simulations. And by and large, what happens is that the simulations tend to have high states and low states in the magnetic field. And when you're close to the high state, the typical resolution of the code is such that it's not doing too badly. But in the low state, the eddy size induced by the MRI becomes small, and the resolution of the code becomes inadequate to enforce magnetic helicity conservation. And so the numbers bounce around almost randomly. So, it's sort of it's not that the simulations are totally unrealistic, but they're doing the right thing probably only in the high state.
Can I ask a detailed question about how did he monitor the magnetic helicity in those simulations?
He didn't. He pulled it out afterwards. That is to say, he had slices. He recalculated the vector potential.
Just by doing like a Poisson's equation?
Yes.
Okay.
Is there a blue light?
Yeah.
Okay, you're on.
And so he was probably using a fairly low order code, whereas someone like Axel is using a much higher order code, and that will make a substantial difference even for a grid code on how well you're going to conserve quantities in a smooth flow. Now, once you've lost the smooth flow, all bets are off, but the MRI should be no more than transonic and subalfanic in the disk. So I think that may well not be a function of grid code, but of which algorithm you're using to evolve your flows on the grid.
I can well believe that. It certainly is algorithmically, dependent on the algorithm to a
Certainly.
very large extent.
Yes.
And I just, more than anything else, I would just like people to keep track of these things before they make claims for the robustness of their results.
That's Glennis?
Talk about whether there's a preference for different geometries. So for instance, in a star, they're not, as I understood the sun, it's not poloidal very much. It's mostly quadrupolar and complicated stuff. Would you see a reason why, for instance, in our galaxy, it would be more simply a, what's the word for the simplest? It's like a dipole, except that it's not.
Octopole? Multipole? Like
No. It's got the topology of a dipole, but it's not got the geometry of a dipole. It's more spread out. It's not compressed like a dipole is. But so what's the name of that?
I'm not sure.
In any event, I've been calling. Okay, fine, great. So I'll call it dipolar.
Dipolish?
But it's not a perfect. Anyway, so my question is not to mess around. Is there some way your analysis gives insight into?
Well, the relative strength of the toroidal versus poloidal is dependent on the relative strength of the large scale shear versus diffusion.
Right, and
but
that part seems to work great in our galaxy.
But if you ask,
why poloidal at all is dipoloidal instead of quadrupoloidal?
right, so the way it chooses between the lowest order modes, I think part of the answer is that in a very flattened sort of pancake geometry, you have a simpler cylindrical geometry, and you have every reason to expect that you're going to have a higher degree of symmetry in the large scale field as opposed to a star where you have a different dynamically related part of the problem, which I haven't talked about, which is that the star has rotation and shear, and the shear is determined in ways I don't understand by the action of the convective zone, and the net result is that the flow of magnetic helicity inside a star is not simply vertical motion, right? It's, in fact, it would appear that most of the magnetic helicity current is recirculated within at the bottom of the convection zone and doesn't ever emerge from the top. And I think that naturally lends itself to more complicated geometries.
Great. I think we should move on. Thank you very much. I could talk about this all day, so I apologize. Is Amir ready? Do you have a microphone and everything? Next up, we have Amir Jafari, who's going to talk about magnetic fields in turbulent environments. Thank you very much.
Thank you. Okay, I'll be talking about magnetic reconnection, not about any particular model of magnetic reconnection. Emphasizing the role of scale and turbulence in this problem, which means that I'm going to use a renormalization group methodology in theoretical physics. To begin with, let me show you this nice video of the solar surface. And that little dot over there is our planet. And remember that on that planet, we have laboratories. And in those laboratories, we have tokamaks and machines, fusion machines, for example, instruments, in which magnetic reconnection occurs. And also it occurs here on the solar surface. And remember that this is, I'm not showing you the whole solar system or an accretion disk or interstellar medium. It's just the sun, a mediocre star. So for God's sake, look at the scales involved in this problem. So scale matters. Scale is important in any physical problem, especially in astrophysics, including magnetic reconnection. And also turbulence. Look at the surface, it's turbulent. In astrophysics, all systems, almost all systems, are turbulent. So In short, scale and turbulence are important in this problem. So to begin with, let me remind you concept of reconnection in conventional sense. What is reconnection? Well, if you have a conducting fluid like a plasma, and you have a large shear or gradient, something like this, in terms of magnetic field, well, what happens is that this configuration is not stable, first of all, and you can have magnetic reconnection during which these antiparallel magnetic field lines will approach. At some point, they disconnect and reconnect again, so the name reconnection. Of course, you can't see magnetic field lines directly. What you see would be these inflows and outflows of the fluid matter. So this is reconnection in a nutshell, and in practice, it's a three-dimensional phenomenon. This is just a two-dimensional picture to give you the idea. So how we quantify this phenomenon? Well, you can say electrons are light and lighter than ions. I can write down an equation of motion for electrons easily, and I'm going to ignore all other non-idealities except for the collision of electrons and ions, which gives rise to this resistive electric field. And it turns out you end up actually with Ohm's law. This is the Ohm's law in terms of resistivity, but you can have any other non-ideality here instead of this term P. Then you know about Faraday's equation from Maxwell's equations. You write down this induction equation, and you're done. You say if, mathematically at least, this P is negligible, it's small, I can ignore that. And what remains here is this term and this, and gives you the evolution of the magnetic field. And then you say, okay, I can integrate and get the flux freezing. It's a well-known theorem, Alfvén flux freezing theorem. And so if P is small, or any other non-ideality is small in your problem, you get flux freezing, apparently. Otherwise, you can tell, okay, this P might be not negligible at some diffuse regions. What about those regions? Well, in that case, you can say this is a non-ideality in my problem. So it gives me some deviation from flux freezing, which means slippage between the field and fluid, which is basically reconnection. So you're done. This is reconnection. You solve the problem. And you move on and say, that's it? No. You have to, in physics, unlike politics, you have to compare your results to experiments and observations to see the agreement. Does the rate that you get from this equation, this is the model that you get this way is known as the Parker model, of course. The rate you get would be very slow, too slow, actually, in astrophysics. In laboratory, sometimes it's good under some circumstances. But again, it's not a very good model. And people talked about this before, you know about this. Now, what's the problem? How can I solve this problem? You say, well, what about other non-idealities? I didn't take care of Hall effect, for example, ambipolar diffusion, anomalous diffusivity, and other non-idealities. You go on, you modify your equations, you take care of Hall effect, ambipolar diffusion, and other non-idealities in terms of this non-ideality term P, the same equation, basically. And it turns out that, again, sometimes it's good in laboratory, but in astrophysics, you fail. It doesn't work in general. So what's wrong with this approach? Well, I told you, scale matters. Turbulence is important. You didn't take care of these two in your simple model. Magnetic reconnection occurs on very, very small scales, in laboratory, for example, also on larger scales, solar wind, interstellar medium, and everywhere, basically. So you have to take care of these two concepts very carefully in a mathematical way. How can we do that? Well, The problem here, by the way, if you go back to this equation here, induction equation, when you neglect this P, basically you are saying that, well, if I have a very small resistivity, I get ideal magnetohydrodynamics. That's it. It's your assumption. Well, do you get that kind of ideal MHD or magnetohydrodynamic equations in general? No. It turns out that mathematically, when you have very small, before getting to MHD, even in hydrodynamics, when you have very small viscosity, it doesn't mean that you have ideal hydrodynamics and ideal equations, because very small viscosity means that you have a very large Reynolds number, and your solutions can be unstable, which means turbulence physically. So with turbulence, particle Lagrangian trajectories would become stochastic. This is very similar to path integral formulation of Richard Feynman of quantum mechanics, if you are familiar with. If not, it doesn't matter. It means that you don't have any unique path trajectory for any particle, any fluid element in that case. In MHD as well, when you have very small resistivity and viscosity, your solutions of MHD equations might be unstable. You're going to have turbulence then, and it means that you have large Reynolds number, large magnetic Reynolds number, again, stochastic trajectories, and MHD equations would become singular. What it means that the very concept of taking derivative would be meaningless. You can't take derivative in that way because velocity field, magnetic field, electric field would be singular fields. So you can't take derivative of these quantities in a normal way. So physically, it means that magnetic field itself would become stochastic. So magnetic field lines in this regime, turbulent regime, don't have a persistent identity at any scale, even at very small scales below the resistive scale. If you look at one field line, magnetic field line, at some instant of time, the next instant, next moment, it's gone. It doesn't have any persistent identity. So it means that, and it's true on all scales, which means that flux freezing is gone. The original magnetic flux freezing. Magnetic field is not frozen into plasma in this regime. Just forget about flux freezing in its conventional sense, which is a very well-established concept in theoretical physics and magnetohydrodynamics, but overlooked by many people. Now, how can we take care of this problem of scale and turbulence? Well, look at this nice landscape. It's beautiful. And look at these clouds. What you see here, of course, are a bunch of clouds. And as a physicist, you can say, OK, I can assign a velocity field to each cloud here. Each cloud moves with some velocity. But if you go put on your glasses or get on a plane and take a closer look, what you will see is that small jiggly-wiggly motion at smaller scales. And if you even closer, you see finer structure, finer and finer details, and more details, finer structure, finer velocity field. So it's not only this large scale velocity field, you have also these components, these fine-grained velocity field. So this also happens in other fields of physics. For example, if you take an electron in quantum mechanics, look at it, it's a particle, right? But if you go to higher energies, which means smaller scales, you're going to see a cloud of virtual particles, vacuum polarization in QED. So it happens in other fields like quantum chromodynamics and condensed matter physics. But anyhow, the concept here is that when you play with this scale, physics remains the same. For example, here, this is a nice picture of Jupiter. And you see the beautiful turbulent environment, the atmosphere of Jupiter. This is the fine-grained picture. You have access to more information, more details. This is the coarse-grained. You are avoiding, little jiggly motions here. You don't have access to them. So it means that you are coarse-graining velocity field, which can be done mathematically by multiplying the velocity field by a rapidly decaying kernel G, depending on the scale you are talking about, and integrate. That gives you the coarse-grained velocity field. You can do the same thing, of course, with magnetic field, electric field, all equations in MHD. So it turns out that, of course, you're going to need some mathematical rules, some conditions for this kernel and the process of coarse graining, but I'm not going to go into details. They're simple and straightforward. But physically, what it means is that the coarse-grained velocity field or magnetic field, whatever, a vector field or a scalar quantity at scale L, for example, for the velocity field, it means that you have a parcel of length L, and this VL is the velocity that parcel moves with. This is the concept, the physical concept behind coarse graining. And as I said, this is basically the idea behind renormalization group methodology, which gives you the mathematical approach to change your scale when you look at your system, any physical system, and how that changing scale would affect your problem. Anyway, this is, in our case, actually, we can do it just by coarse graining, and the idea is that physics doesn't change, actually. With your eyesight, obviously. This is the idea. Next, in MHD, in our problem, magnetic reconnection, you have this induction equation, this non-ideal term. You coarse-grain the equation, and you get a coarse-grained version. This is, for example, in QED, people call this normalized equation. This is called Bayer equation because it's not coarse-grained. This is the fine-grained version. It means that, in this case, this non-ideality derives reconnection, the slippage between fluid and field at small scales. You were right about this non-ideal term on small scales. It's the driving force behind reconnection. But when you look at this equation and compare this term, this new nonlinear term, which is given by this expression, and compare it to this non-ideality, you see that this term is negligible at larger scales. It's gone. It's very small. So it means that in a coarse-grained version, you have to look at this non-linear term, and you can ignore the non-ideality. This is the point here. Now, I'm going to give you an example here. It's a numerical simulation. It's an incompressible homogeneous MHD simulation. If you are interested, you can find more details in this paper here. It's coming from Johns Hopkins turbulence database. Obviously, here you can see a reconnection event. Why? Because you can compare to this cartoon I already showed you, and here you have almost the same thing because you can identify this symmetric reconnection. You can see, of course, a large-scale current sheet, not shown here. And you can identify outflows along magnetic field lines and also inflows. So it is basically reconnection. It's not voodoo judo. It's not magic. It's the same concept. But there are differences. One difference is electric field. This picture on the left shows the different components of electric field. For example, the red curve is this ohmic electric field as a non-ideality. At smaller scales, which means fine-grained picture, mathematically, this is large. This is driving magnetic reconnection. You can measure it in your simulation. But when you coarse grain at larger scales, this term, this non-ideal term is gone. It's very small, negligible. But this non-linear term coming from turbulence, motions below the scale L, drives reconnection. So the point is that at smaller scales, non-idealities are important in reconnection. At larger scales, turbulence itself, non-linearities. So, conclusions. I should stop talking, but just a minute. Small resistivity and small viscosity don't mean ideal MHD. Be careful. it means that your solutions might be unstable, and you're going to lose the meaning for derivative. Your equations are singular, and the fields, magnetic, velocity, electric fields, are stochastic. Small resistivity and viscosity, small the turbulent transportation coefficients don't mean flux freezing. Flux freezing is gone. In turbulent regime, you don't have flux freezing. Magnetic field is not attached, frozen in to the plasma. Reconnection is driven on a wide range of scales. I showed you there's a wide range of scales that magnetic reconnection occurs in nature. And also, at small scales, perhaps in laboratory, for example, resistivity or any other small-scale physics law, like Hall effect, I don't know, hemipolar diffusion, whatever, under appropriate for your system, can drive reconnection. But at large scales, it's turbulence, non-linearity inherent in the Ohm's law that drives reconnection. Thank you very much.
Thank you very much. That's super interesting. Blakeslee?
Yeah, I'm just wondering if there is a transition between, you talked about like a turbulent regime and then the non-ideal effects. Is there a transition, and is that transition somehow related to the properties of the large-scale field wandering, or what's your view on that?
Well, a short answer is that when you look at the small, well, you have the coarse grain in your equations, and your question is, what's the transition between fine-grained version of these equations, for example, in MHD, and large coarse-grained version and the same equations? What happens is that this term that I show, where's R? This term, this is the non-linearity coming from when you coarse-grain, it appears in your equations. When you go to smaller scales in turbulence, it's going to get larger and larger. At some point, for example, below the initial range, when you have the viscous scale, this RL would be comparable to this. So at the transition, non-idealities and non-linearities are of the same order. So this way you transition from coarse-grained or fine-grained or vice versa.
So like the growth timescale from the nonlinear terms is large compared to like diffusive timescales from the small scale physics?
It depends on which scale you mean, and that viscous scale?
Your A to J. That's your resistive scale, right?
Yeah.
So when that is no longer sufficient to damp out nonlinear terms, that's when the transition happens. Is that right?
Yeah.
Okay.
At smaller scales, you can ignore this RL, and this non-ideality would drive your reconnection.
Cool. We have a minute for another question. Alex?
Well, you claim that you are not supporting any particular model. I guess that you are supporting one model.
Yes,
and,
obviously. Yes, I'm supporting a stochastic reconnection, LV99.
Yes,
it's an agreement with
well,
that model.
my question is, this was just joke. My question is it easy to distinguish the situations when plasma effects are important, like, for example, in magnetosphere, from the cases when plasma effects probably are subdominant, like I believe at least in the interstellar media, probably in the solar wind. How can we use this approach to go from one physical regime to another regime?
Well, it goes back to the same question about transition regime. For example, when, at which scale, basically, this term and these two terms are comparable. And when you have resistivity, for example, I would say on the viscous damping scale, but if you have other non-idealities, like Hall effect, for example, you have to compare, you have to write down equations and compare that non-ideality, coarse-grained at that scale, to this non-linearity given by this equation. So it's basically about scale, but the short answer, I think, is that at larger scales, when you are in the inertial range of turbulence, all non-idealities would be negligible. You can ignore them, like in interstellar medium, for example.
Well, thank you very much. Our last speaker for the day. Oh, sorry, let's thank Amir again. Our last speaker for the day is Laurel Fizzle, and she'll be talking about the relationship between magnetic fields and molecular cloud structure. Thank you very much.
Okay, is my microphone working?
Is it on?
It's on. I pushed the button.
Do it a little closer to the mouth.
Okay, is that better? Okay, good, cool. And where's the stick? Ah, yes, cool. Okay, great. So thank you very much to the organizers for allowing me to come here, even though I wasn't entirely sure whether I would be on this continent when the meeting actually took place. So I'm going to tell you what we've been learning from detailed maps of magnetic field morphology over the past couple of years, and what that's telling us about the relationship between magnetic fields and the structure of molecular clouds. Okay. So one of the things that makes studying the role of magnetic fields in star formation so complicated is that star formation actually really takes place over a huge range of scales. So into kind of zeroth order, you can think about it as the problem of getting from very, very diffuse scales, compressing gas from the ISM, creating molecular clouds, which are much denser, then into the finer structures, filaments, clumps, and then down to cores and protostars, and eventually to stellar systems. Okay. So if you think about it, you can sort of break this down into two kind of crude problems, okay, in terms of the efficiency with which we convert gas into stars. And so the first is, how efficient is it are we at converting gas into gravitationally not bound structures to gravitationally unstable, to really denser structures. Okay. And then the second part is, how efficient is the process of converting these gravitationally unstable dense gas structures into stars. Okay. So in this talk, I'm going to focus on this first problem. In particular, how we form structures within molecular clouds, and what observations tell us about the relationship between that and magnetic fields. Okay. So I'm going to start off by talking about observations that we have of magnetic fields in star-forming regions, and show that we see a real correlation between the structure in the magnetic field and the structure that we observe within molecular clouds, and how that implies that the magnetic field is both quite strong on large scales compared to turbulence. It's at least in equipartition. And then I'm going to talk a little bit about how, at least in one cloud, we have hints that this orientation of the magnetic field with respect to the cloud structure also seems to be correlated with the local star formation efficiency within that cloud. Okay. And then finally, I'm going to talk about how, to really understand this, we need much larger scale surveys. We need really detailed maps of many, many clouds, and some of the telescopes that are coming up that will allow us to make really detailed maps of magnetic field morphology. Okay. So to start off, we have seen in simulations for a while that there is a correlation between the magnetic field structure and the cloud structure. Okay. So this is easy to observe when you look at these simulations. So this is work from Juan Soler's thesis. Okay. And on the left is a weak field simulation. On the right is a strong field simulation. And you see very clear differences in both the magnetic field morphology and the relationship with the structure. So in the weak field simulation, you see that the magnetic field is much more disordered. You also see that the magnetic field tends to be aligned parallel to these structures that are formed. Okay? And then in the strong field simulation, not only do you see that the field is overall more ordered, but you also see that while at low column densities, the magnetic field still tends to align parallel with the structures. At high column densities, these structures tend to align perpendicular to the magnetic field. So we can look for these same trends in observations, and then make detailed comparisons between the simulations and the observations, and use that to constrain the magnetic field strength and to learn something about how magnetic fields affect the formation of molecular clouds. Okay. So a nice illustration of what's going on here is from the paper by Philip Motz and Blakesley Burkhardt, which was discussed earlier this morning. Okay, so what happens is, what they find is that where you have magnetic fields, you form these long shocks, which are parallel to the magnetic field direction. Okay, and these tend to sweep at material. And what you see is that the material, this was mentioned this morning as well too, so this might be a little bit hard to see. But if you have a core at later times and you use tracer particles to see where that material that's eventually going to go into this core comes from at an earlier time step, you see that the material tends to accrete along the magnetic field direction. Okay? And then that ends up forming this denser structure, which is perpendicular to the magnetic field. And so by a crude analogy, you can sort of think of the magnetic field as kind of acting as like the guardrails on a water slide or something like that, right? It's not setting the, it's not driving the motion, but what it's doing is it's adding kind of a potential energy barrier to keep the material from moving in the direction perpendicular to the magnetic field lines.
Hopefully no shocks form in this.
Yeah. Okay, so if we want to actually test to see whether, yeah.
When you say that they form shocks parallel to the field, you mean they're moving parallel to the field. So the shock sheet is perpendicular, but the shock normal is parallel.
I think that's right. Do you, Philip and Blakesley, do you want to comment on that? Yeah. Okay. All right. So we can actually test this with observations and compare to what we're seeing in simulations by making really detailed maps of magnetic fields through dust polarization. So dust polarization, because dust grains align with respect to the magnetic field, we can use their polarization to map out the magnetic field morphology. Okay, and so we can look at this in different regions. There have been a lot of really great advances in polarimetry in recent years. So there are new polarimeters like POL2 on JCMT and the new HOT Plus polarimeter. And then, of course, Planck has observed the whole sky. The problem is Planck has fairly coarse resolution, and these other polarimeters are really still limited by the atmosphere. So, for example, a single Planck beam is larger than this entire map with SOFIA or with HOT Plus. Okay. So if we want to look at large-scale structure of molecular clouds, then really Planck is a good place to start. Okay. So this was done by the Planck collaboration, where what they did is at every point in the cloud, they used the gradient of the column density field, and then they compare that to the local magnetic field orientation that they infer from polarization. Okay. And this gives them an alignment angle between the cloud structure and the magnetic field at every point in the map. Okay. And so if you bin this by column density and you calculate an orientation parameter, so the details of this aren't too important, but basically if it's greater than 0, then the alignment is preferentially parallel. If it's less than 0, then it's preferentially perpendicular. Then what you see is that most of these clouds, in fact, in all of them, there's a trend of decreasing relative orientation parameter. That is that at the lowest column densities, they tend to be the most parallel. And then this relative orientation decreases and becomes more random. And in most clouds, it actually crosses over to perpendicular, okay, at high column densities. So if you sort of combine all of these observations, that's what these gray points are in the backgrounds. This is a slightly different parameter. And then you compare these with the simulations that I was showing earlier of what you get looking at synthetic observations from MHD simulations of molecular clouds. You see that the weak field scenario really can't reproduce this change from parallel to perpendicular, or even crossing to no preferred orientation, which is at 0. Okay? These observations are much more consistent with either intermediate field strength, which is where the magnetic field is roughly in equipartition with turbulence, or the strong field case, where the magnetic field is stronger than turbulence. Okay. So the Planck observations, Planck really only had the resolution to do this for the very nearest clouds, which tend to be quite low mass. Okay. So we can do better, and by building a new polarimeter, which operates from the stratosphere. Okay, so this is the view that you get from a stratospheric telescope. So you can really see the advantage, which is that you're basically above more than 99.5% of the atmosphere. Okay, so this is the blast pole telescope that I and Giles have worked on a lot over the past couple of years. Okay, it has still fairly coarse resolution, so 1 arc minutes, but really we had to smooth to more like 2.5 arc minute resolution, but that's still 4 times better than Planck. Okay, and this allows us to actually map out more distant giant molecular clouds, which are more representative of where more stars form. Okay, so this is the region that we made the best map of. This is the Vela C giant molecular cloud. It's very cold. It's very young. It's in early stages. I can't read that. Okay. Okay. All right. Sounds good. Okay. And so here is our map of the magnetic field morphology. And we have the most detailed magnetic field map that's yet been made. There are over 1,000 independent measurements of magnetic field direction. And so what we find when we look at the blast pole data is something quite similar to the Planck, okay, except now we're extending to much higher column densities. And so the blast pole data is mostly consistent with having either no preferred orientation or perpendicular. Again, mostly consistent with this, the magnetic fields being at least as strong as turbulence. Okay, so the conclusions from this are that the large scale, cloud scale magnetic fields have are fairly strong, and that they're at least as strong in terms of energy as turbulence. Okay? And this means that they're strong enough to influence the formation of cloud structure. So we can go a bit deeper with this map by actually comparing not just to the column density that we get from dust, but looking at individual molecular lines. So with for the polarization, we're actually, because the dust is optically thin, we're sensitive to the entire cloud. We can see through the entire cloud. But if we look with different molecular line tracers, we're going to be picking out certain density regimes within the cloud. So we can look at a tracer like 12CO, which is very abundant but quite optically thick. Okay, so we will only see the outer envelope, the low density regions of the cloud. Or we can look at a more intermediate density tracer like 13CO, which is looking deeper into the cloud. Or we can look at tracers which are really only excited in the higher density regions, which are really isolating the higher density regions within the cloud. So we looked at 9 different molecular lines, each tracing different regimes, density regimes with a MOPR telescope, and compared that with the blast pole results. So here's what the maps look like. Okay, you can see the 12CO, you really don't see much of a filamentary structure. You're mostly just seeing the envelope, whereas some of these higher density tracers like HNC or N2H+, you see a lot more of the filamentary structure. And what we find is that you get very different relative orientations for these different molecules. So the 12CO, which is tracing the lowest density material, is very parallel to the magnetic field. Whereas some of these other tracers, for instance, like ammonia or these higher density tracers, they tend to be perpendicular. So what we're seeing is, if we translate this into a rough estimate for density, we see that this actually corresponds to a change in relative orientation with density. So low density material tends to align parallel to the magnetic field, whereas high density material tends to align preferentially perpendicular to the magnetic field. Okay, and this crossover seems to happen somewhere around 1,000, although there's a lot of uncertainty. Okay. Okay. So what this is telling us is that the large-scale magnetic field not only dictates the or influences the structures in the low-density regions of the cloud, but it actually seems to be correlated with the structures of the much higher density regions, which are on much smaller scales than the magnetic field that we're actually probing. Okay. So could this mean that the magnetic field actually could affect the formation of the star formation efficiency locally? Well, we can look at the different regions within Vela C. So in particular, there's this region up here, the center ridge. Okay, this has most of the protostars, which are massive protostars, which are shown in black. It also has an H2 region here. This is the warm dust for that H2 region. Here's a picture. This is the RCW36 region. It's the most active star-forming region in Vela C. Okay. And if we look at this relative orientation, we see that the center ridge, so this region with the highest star formation activity, has a very different structure than any of the other regions. So it's very perpendicular in almost all of the tracers, and even the 12CO is still not very parallel. Okay. All right. So what could be happening? One possible explanation is that if the cloud formed, so we know that that these regions probably formed from converging flows. Okay, if those flows were aligned preferentially parallel to the magnetic field, then they would have been more efficient at forming dense gas. Whereas if the flows were aligned with a significant offset to the magnetic field, they could have been less efficient at forming dense gas because they had to move across the magnetic field lines. So it's possible that that could be what we're seeing in this center ridge region, but we really need to observe a lot more clouds and see if this is actually something that's consistent with in many different regions. Okay. So to do this, we've been building BLAST TNG. So this is the next generation BLAST. It will have a 10 times increase in mapping speed, 5 times increase in resolution, and a much longer flight time. Okay, and we were hoping to fly it this past winter. That's actually, I was just in Antarctica a week ago. This is about as close as we got. This is BLAST TNG on the launch pad. And unfortunately, the winds picked up. This was our last launch attempt before the stratospheric wind patterns broke down. So BLAST TNG is currently strapped down and waiting for us to return in Antarctica. And so we should be able to fly this in December 2019. And then just to finish, we also have a number of proposed satellites which could make even more detailed maps of even larger numbers of clouds. So that's something to look into, and if you're interested in that, please come talk to me. And so I'll just I guess I'll just leave at my conclusions and take questions. Thank you.
Thanks very much. Mark?
Star formation efficiency, let me urge you to be a bit more quantitative, because, I mean, saying, all right, there's active star formation here, what I would consider convincing evidence for some effective magnetic fields on star formation efficiency is if you can show epsilon FF is systematically different. All right, what I mean is that, right, denser stuff forms stars faster. That's no surprise. Denser stuff has a shorter dynamical time. So to zeroth order, it seems to me like you could just explain your result as, well, all right, both magnetic geometry and star formation rate are correlated with density, and that's the underlying variable, and there's no physical relationship whatsoever. They're just both correlated with density.
Okay.
So if you want to, have you looked at specifically epsilon FF and its dependence on magnetic fields?
So we have looked at the column density PDF, right, which is related, but we haven't actually quantified epsilon FF. So the column density, that center ridge region does have much more of a pronounced column density tail, power law tail at high N. Okay, so but we haven't calculated that. I think I agree with you. I'm not saying necessarily that the magnetic fields are supporting or influencing the star formation. I'm saying that the geometry of the field with respect to the formation flows may have affected how much dense gas you were able to form.
Okay,
it's only one cloud, and we need to look at this in a lot more clouds.
Right, I just want you to be very careful about. I have seen a huge number of papers over the years saying blah causes efficient star formation when the correct statement of the observational result is blah is correlated with density and stars form faster in denser gas.
Right, so I think that goes back to what I said at the beginning, right? There's sort of the question of how efficiently do you form dense gravitationally unstable gas? And then there's the question of how efficiently can you convert that into stars, right? And so this would be the first scenario. This is saying that you can more efficiently create dense gas.
Okay. Yeah. Other questions? You?
Observations, the turbulence inside the filament is superauthentic or subauthentic?
From the polarization observations, I would say that we don't have that because I don't think the blast pole data, this cloud is at like a kiloparsec. And the blast pole data can't resolve the filaments so far. With the new blast telescope, we should actually be able to resolve these filamentary structures, and so we might be able to say something. And there are also other telescopes that have higher resolution that should be available soon that will be able to tell us more about the magnetic fields within filaments. Yeah.
Alex?
Some concerns with your theoretical picture that you showed with this converging flows.
The cartoon I made in 10 minutes on the plane?
I don't like converging flows idea at all, but it's not the reason why I'm asking it. You know, the main assumption in this picture is that you have, you know, stable, fixed magnetic fields, and you move your clouds. And in fact, what we are having in a realistic situation, exactly because we have turbulent eye connection, we have these mixing motions, which are acting perpendicular to magnetic field. Magnetic field is turbulent, and therefore it explains, and Xiao did the work on that, how you can create this low contrast filaments along magnetic field.
So I agree with you, but that's a lot harder to draw in a PowerPoint cartoon.
Okay.
And the other thing is that you must have some kind of converging flows, right? Like that's how you accrete the material, right?
Well,
it might not be as simple and laminar as what I drew in that simple cartoon. But if the flows are aligned with respect to the magnetic field, that's going to affect the properties of, for instance, like the shocks that form.
Yeah, these are the big edges which have their magnetic field, and this when these edges interact, you create on these intersections the flows where, yes, you can accumulate material.
Okay.
All right, I think we should cut it off there. I want to thank Lara and everyone else in this session